Hopefully people can see the slides.
Yes.
All right, guys. So, hey, so a small clarification from yesterday. There was a bit of confusion in the loss and the cost, right? So, let me clarify. There was a small mistake from my side, right? Okay, so first what we discussed was correct. Yeah, not the second one, right? Now, basically, a loss is for a single input that you give, right? So, for example, I give an input x1 and I get an output y, right? And y can be two-dimensional. Let's say this is a vector which has, for instance, probability values for cats and dogs. Let's say it's an image of a cat, and this is output for, say, the probability that is a cat, and this is a dog, and then it's saying 0.1 and 0.5 or something like that, right? It's saying 0.1, with 0.1 probability it's a cat, and 0.5 it's a dog, so it's making a mistake, right? So what we can do is, at this output space, right, for this particular input, the value should be, so if this is the dimension for the cat and for the dog, so it should be high here and low here, right? So the point should be somewhere here. Instead, it is somewhere here, right? So there is an error, right? So this is a loss, right? So this distance is your, basically your loss, or the amount of error that you have in the difference between cat and dog. That's your loss. That is for a given input set, right? Now, in essence, what we can do is we can write that as something like y minus y hat, the whole square, for that particular image, right? So the error is something like that. Okay. Now, in fact, if we have something called mean squared error, which will be over many such images, n, now that's something like your cost. Okay. So this is the average over several of such inputs, right? So x1, x2, x3 to xn. All right. So that is going to be your cost, and you can use, so as we discussed, when we are updating sequentially for one input at a time, then we can use the loss function to update the, the parameters of the network. And if we take a bunch of inputs and do what's a batch update, then we are doing what's called a cost. We are updating using the cost. Okay. So that is what how we discussed yesterday, but in the middle there was some confusion. Sorry, my bad. Okay. Is this clear? Any questions here? I thought I wanted to make this clear before we moved on.
So can you give me again, like what you explained about batch update?
So batch update is when you take many such images, right? Let's say, and then you feed it to the network, and you will get at every point a loss, right? Right? You
L1,
can
L2,
calculate
L3.
L1, L2, L3, right? Now, what L1, L2, L3 is nothing but these individual ones, right? These ones. And if you sum it over, say, a certain set of inputs, you get what is your cost. This is your cost function, right?
Yes.
And then you can use that also to update the network in one go, and which is often what's called batch update. So if you're updating sequentially, then you use your losses. If that is the case, then you are slightly sensitive to outliers as well, because let's say, imagine if this is your space of, this is your input space, right? Let's say input feature space is x1, x2. These are the features that define, say, cat and the dog. And then you have a bunch of points that correspond to cat, and then there's some outliers as well. And then there is a bunch of points that correspond to a dog, right? And there's an outlier. And you want to probably separate these two things. Now, what will happen is, if your initial input is here, right? Now, the network will optimize itself so that it is able to separate this out first. But then for inputs that are belonging to the cloud or the points here sequentially, it will adjust in such a way that at the end of the day, you might not be able to, separate these out really well. Maybe your separating or classifying line becomes somewhere very close. So there's still ambiguity in terms of what is what, right? But if you use the entire information, then you might be able to create a better boundary for better classification, right? So the sensitivity to outliers, because to certain outliers, the things might be, if it's a point there is somewhere there, then this plane or this line that is separating these two classes might become very unstable, right? But then if you are using a collection of all the losses, which will become a little bit more predictable about where the class of cat versus dog lies, which is these sort of clusters, then that might give you a better separation, right? So that's the difference between using a cost function and a loss function, right? So there are advantages to that. Okay, so I think that is what I wanted to clarify before we start today. If there are any more questions, just let me know.
Sir, maybe not related to this topic, but
Yeah.
there is one concept called epoch.
Yes.
That is equivalent to this batch update
Batch.
only, right?
Exactly. Correct. Exactly.
Okay.
Yeah. The epochs are basically a set of inputs that you give to the network, and that forms one epoch, right? And that is, once you give that epoch to the network, then you do a batch update. So the update is the epoch is the forward pass that you give to the network and see what the output comes. The batch update is the backward pass. That is, you take the information and then you update the parameters. So yes, you are right. So it's the equivalent.
Sir, epoch means one epoch is equivalent to one forward plus one backward, or maybe
I think there is one forward plus one backward is one epoch.
Okay.
Yes, it includes the batch update. So when you say these many epochs were trained, you are trying to say you push these many inputs in and then train those same inputs in that epoch. That's what you mean. Okay. All right.
Okay.
So let's move forward. We saw this. We were looking at gradient descent, right? And we were talking about some ideas of stochastic gradient descent and how that works. And in fact, we kind of were here at the last step where we were talking about global versus local minimum, right? And the idea is very simple. Like if you have an objective function or a cost function that you are trying to minimize, the landscape of the objective function with respect to your parameter space, right? So let's say the weights or the biases might have very complex terrain, right? Something like that, let's say. Okay. So there are many pockets here of places where the function becomes minimum, right? Like there are certain pockets here, there's a minimum here and here. Typically, there is one location on the function where the function is absolutely minimum, which is often referred to as the global minimum, right? This is the global minimum. But there could be other locations as well where you could end up if you are trying to optimize depending upon where you start off from, which are often referred to as local minimum, right? And our typical aim when we are trying to solve for a network's parameters is to make sure that at least we are able to reduce the errors to such a level that our problem or the solution to the problem works, right? That's number one. But we are also trying to establish ways in which we can find the global minimum, because that's where the function tends to go to the least value. But sometimes reaching the global minimum might not be a possibility. It depends upon things like where you start off from and how much amount of noise is there in the system in order to prevent it from settling down into these shallow grooves, right? Like as we discussed before. So there are certain ways like stochastic gradient descent, like we were talking about, where individual changes in the objective function will not be will not be smooth. They'll be very noisy, giving you some sort of a latent push into this space, right? So even if you are here, yeah, the random noise might push you over this cliff, and that way you can end up into the global minimum, for instance. Or if you are here, then into this. Okay. So that's the idea behind gradient descent. There are many ways in which we can implement it. I wanted to show you guys an example with a simple perceptron initially and establish this, because if you get this basic idea initially, I think then understanding networks at a larger level will become a little bit more easier, right, and more intuitive. So I was thinking, let's talk about a simple example with a perceptron with two inputs, right? And so you'll have two weights and a bias and an output, a single output. And let's say this is my feature space, right? X1, X2. I have a classification problem, right? Where I have 3 in one class and one of them in another class, right? And my inputs are Boolean in nature, right? So I have 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So this is a basically Boolean logic that we are trying to solve with perceptron. So is this problem linearly separable in the first place? Yes, no?
Yes, sir.
Yeah, yeah, right? Because probably you can draw a line here and separate these two things out. Okay. So and a perceptron works well. I'm just using this as an example to establish how simple things like backprop as well as simple delta rule and how backprop works and how it can be expanded to an entire network. Right? But it's a very simple problem. But so what will be the equation of the perceptron? So y would be equal to f of w times x. I'm sort of writing w as a vector, so w transpose x plus some bias p. Right? So this gives you, this is nothing but sigma over all input space I, wi xi. Okay. So training a perceptron is very simple. All you have to do is give the input x. You want to train for the parameters wib, you get your y. You have your error or the model predicted, and then you have your desired input that's coming in. And then you have your error, you're feeding it back to the network to kind of train the weights. And how do you do that? How do we derive this? Right? Let's derive this rule. And Frank Rosenblatt was the first person to kind of help us understand this training of the perceptron. So this is what I wrote, right? So typically you can, bias is subtracted. You can also add it. It's fine. It does not matter. The sign will change at the end. So it can be wxi minus b or plus b. Okay. So x is belonging to the range of real numbers. So we are in the real space. Okay. So xi is 0 and 1, right? So this is your 2D space, and then yi is either 0, 1 here, because what we want is one class. Let's say this class is 0 and then this class is 1. Right? So what is this in electrical engineering or other stuff? What is this basically?
OR gate.
Yeah, it's a logic gate, right? So it's an OR gate. So we're trying to solve a gate here, and we can understand most of the principles of how the network works with this simple stuff. Okay, so let's talk about the loss function and its minimization. As I mentioned, the loss function for a given input, right, would be the error into 1 by 2 into t minus y square, right, desired minus what the output of the network is. So for a single pattern p, right, you have this EP is 1 by 2 dp minus yp. So given one particular pattern, let's say 0, 0, or 1, 0, so 0, 1, right? You have a particular output, right? In this case, it's 0. In this case, it's 1. So when the network is initially untrained, we'll have an error. And this is the sum over all errors. This is basically your cost, right? This is your cost. So all patterns P. Yes. Pretty simple. So that's the case in this particular problem. And so for a pretty much a linear neuron like this, what we can do is we can take and start deriving what will be your change in the parameters as a function of the error, right? So error is dp minus yp the whole square. Yp is nothing but this, right? G into W transpose XP, which is for given pattern minus the bias, all right? And if I take this to be something like H, which is nothing but G of H. Now we know that this error function is quadratic in nature. That means we know that it looks like something like this, where for a given input space, this is not the same X as this is an input space X, right? In our case, this is our parameter space W. We are trying to do gradient descent. That means what we are trying to do is that we are trying to find out the change in X, and we are looking at the gradient of this function f of X, right? And then we are moving towards the negative of the gradient, right? So that means that we are trying to find out the direction like this, right? So we are trying to find out the slope at every point, and then we are taking the negative of the slope, and we are trying to go down that gradient, right? Whereas in this case, so you might ask what happens here. So for example, here the slope is negative already, and what you want to do is you want to move towards the opposite of that. That is, you want to move, because if you move towards the negative, then you move this way, but you want to move towards the other side, right? So minus of minus, so this way you'll move. So you want to come down to this point, the minimum of the function, and you always want to follow the negative of the gradient. So this is how you do the gradient descent. So the change in the parameters is a function of some eta times. This could be something like learning rate. That is, you do not want to step down really, really fast. You want to do it incrementally. That is, you don't want to immediately jump across, but you want to do it in a way that's smooth, so that it does not lead to any instability, right? So that's where you add this small learning rate. And in this problem, we look at how gradient descent works, and you are able to go down this error function. Okay. So you want to move down the gradient. So how do we use gradient descent to estimate the parameters, right? That's what we need to know now. Now, if this is your error function, and this is what it is, right? What do we need to do in order to get to the parameters? What do we need to find? Any idea? What do we need to do to this function?
Differentiation.
Yeah, differentiate with respect to what?
X.
With
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 respect
respect
to
W
Sorry?
parameters. W?
Yeah,
Z,
with
Z.
respect to W.
Oh,
Yeah.
sorry. Yeah, did.
Yeah, with respect to W, you are correct. So we need to do it with respect to W, because we want to know how the error changes as a function of change in W, right? That's what we want to find. So if I go back a little bit here, this is what we want, right? We want the change of the error function with respect to W. So we need to differentiate this function with respect to W. So let's do that. So if I take this to be H, and let's take this formulation, let's do that. So I want to do, you want to do partial differentiation, because we have two parameters here. So dou EP by dou W. What would that be? Any idea, guys?
2 times
Yeah.
sorry, dp minus, no, sorry,
2
dp
times.
minus
Yeah.
dp minus
Yeah.
gh
G of H
into
into
uh, w xp
XP.
xp.
So first, before that, chain rule of differentiation, what do you have to do?
Yeah, so you have already applied on gh. Now we will going inside the gh.
Yeah, but you have not applied yet on GH, right? So
We
there
are
is going
applying
to
on
be
now.
a
Yeah.
G dash of H, right? So
Yes.
you have to differentiate G dash, and now you can go inside H, which will be
xp.
right?
XP
XP.
Yes.
minus XP. No XP.
Next.
XP. Okay, right? Now this is nothing but we know y, right? So 2 gets cancelled, right? So this is dp minus yp into g dash of h into xp. So in some sense, this is, if g dash of h is some sort of, we can take this as a proportionality constant, right? The gradient of the function, because if we take a nonlinear activation function here, something like a sigmoid function, which is continuous and differentiable, that can be taken or absorbed. So this is sort of proportional to dp minus yp times xp, right? So basically the change in the change in the error function as a result of change in w is proportional to this, right? So this is this. So how will you update your w then? Any idea?
W minus
Yeah,
eta times
yeah.
dep dw.
So you want to go towards, so okay, there is a -1 here, right? Sorry. When you differentiate g dash of h, there's a -1. Yes. So what you want to do, you want to move towards the negative of the gradient, right? That's the idea. So if this is the gradient with respect to w, you want to go towards the negative, then minus of minus will become positive. So that means the change in w, delta w, is nothing but minus eta times dou ep by dou w, right? So which is equal to eta times dp minus yp into xp, right? So that's your update rule for w, right? So the change in the w at every pattern that you present is nothing but the error multiplied by your input. So that will change the weights appropriately. So that's the first for w, right? Simple. You just have to differentiate, and now you want to move towards the negative of the gradient, and you get this update rule. Any questions here? If there are questions, just let me know. Okay. All right. So if there are no questions, then I'm going to erase this because we'll do the same thing for the B or the bias. Okay. So what will will this same update route for bias? So if you do dou EP by dou B, that'll be
2 by 2
2 by 2 again, right?
dp
dp minus yp,
g.
yeah, dot g dash of h times -1, right? And this time,
Yeah, no XP.
and then no xp, but
Yeah.
what is
Minus
the
b.
differential? Minus b
Minus
or
1. Minus 1.
-1. Minus. Okay. So this is going to be then dp minus yp into g dash of h. All right. Or it's proportional to dp minus. Right. So the change is nothing but the error itself. Right. So then now the change in the parameter delta b is going to be minus eta dou ep by dou b. So change in b will be minus of dp minus yp. Oh, sorry, eta times. So that's the update rule for your bias, right? Any questions here? Is this clear? Right. So that error has now been propagated back through the network, and we have now estimated our biases and our parameters, our weights and our biases. Okay. So that's what I'm putting it here. Right. That's that. Okay. This is what we were deriving. All right.
Sir, I just have one question.
Yes.
Clarification rather.
Yes.
So bias is not a constant, it's a function.
It's a parameter, right? Bias can also change. In fact, the bias, if you remember from the activation function, right? So if this is your x and this is your activation function, y equals f of x, which let's say it's a sigmoid, right? Something like that, right? Now the bias can shift this function, right? Either towards the right or towards the left, making it more sensitive towards the input. So there is a that is also a parameter then that you can vary in order to make sure either the neuron responds with even with the smaller input, can it respond higher, or with only increased input can it respond higher, right? So you can change this curve basically. So that is also a parameter, not just the weights. In fact, sometimes the bias term is absorbed into the weights. In fact, you can think of bias like this too, right? You can think of bias like an additional input x3, which is always 1 but has a weight b. Okay. So in fact, that is then also thought of as a parameter. So there are multiple ways of representing it. Sometimes when you represent it this way, it becomes easy because then, it's like another parameter into this network. So the input, instead of just being x1, x2, it will be x1, x2, and then 1 all the time. Right?
So does it mean that when we are changing the weights of the input, so at that particular point, we are also changing the bias parameter?
We are
if
doing
required?
everything at the same time. That is, when we, for a given input set, when an error gets generated, I'll show you a script right now which will make it all very clear. But for the given error, when you back propagate that error through the network, you update both your weights and your biases. In fact, for a perceptron, it's not called back propagation, it's mostly called the delta rule. But it's the same idea even if you go to a bigger network. I'll show you how it works, how the math works when you go to a slightly deeper network. But the concept still remains the same. In fact, you should think about it like this, right? If this is the error, right, you are taking the error, pushing it through the network. If you have to push it back through the network, first you have to push it through this function, right? If you have to push this through the function, that's this part, right? The gradient of the function. And then what you're doing is, after you push this out, you can distribute it to the weights and to the biases, right? So you're sort of taking the error and then pushing it back through the network.
Thank you, sir.
Okay, cool. All right, guys. So any questions here further? So if you get this idea, then it's easy to understand that now the change in W will be nothing but W new will be equal to W old plus some eta times your delta W. Right? So your new weights will be your old weights plus the change in the weights with some learning factor. Right? And that way you can update the parameters of the network. So that's basically that.
Sir, for a single perceptron, we can call this as a forward feed forward network, right? Sir?
Yeah.
Then
So
why
this,
you are talking about back propagation?
And since because you have the error, every feed forward network has a forward pass and a backward pass, right?
Okay.
Right. So we have not looked at the backward pass yet for a big network, but if you understand it in the perceptron, it becomes easier to understand in the big network, right? So here forward pass is you push the inputs through the network, you get your output, you get your error, and you take the error and you push it back through the network to update your parameters.
Basically, we need to call this as the feed forward network, right, sir?
It's a feed forward network.
Yes,
after training, obviously you want to test it in the feed forward way, right? Like once you train this, you want to give new inputs and see whether it's able to do this. But this is a very simple example just to contextualize it. But typically that's what you want to do. So that's the feed forward nature of it. Okay. All right. So, and what you can see is, if this is the error, right? And the error will sort of decrease across time. This is how you would see the gradient descent working, right? Because for gradient descent, what you want to do is you want to minimize error across time. So when I say across time, for every pattern that you present, you want to see that the network's error starts reducing till it stabilizes at some low value, okay, or approaches 0. Okay, so what I will do now is I have written a small MATLAB script. In fact, the rest of the course we will actually do it in PyTorch, but I thought for visualization I had written a simple script and it's easier to get it, so I did not want to rewrite this in another
Sir, a
language.
small question.
Yes.
Yeah. So, what is your perceptron? It's a kind of like a one neuron or like
It's just one neuron. It can have, in this case, it has 2 inputs. It can have multiple inputs too, right? So, but it's just one neuron, just one layer, right? There is no hidden layer in here.
Okay.
That's what makes it a perceptron. If there was a hidden layer here, right, then that makes it an MLP. So if there's a hidden layer before it went to the output, that
Then
makes
it's
it
going
a multi-layer perceptron, right? And then you have many more layers of this, then it is a deep learning feed-forward network.
Okay.
Right? Yeah. So it's just an extension of this, right? So if you understand the idea here, then the extension becomes more intuitive too. Okay. Right? Okay. So let's look at a script that I wrote. Hopefully people can see this to solve the Boolean logic. So people can see this? Yes?
Yes, sir.
Okay. So what I've done is, maybe I'll increase the font size slightly. So that. Okay. So what I've done is simple, right? I've defined some inputs, right? 0, 0, 0, 1, 1, 0, 1, 1, right? And I have like three different types of logic outputs that I want. Forget about this for a moment. I have an AND gate where the outputs for each of them is either 0, 0, 1 is 0, 1, 0 is 0, and 1, 1 is 1. And then for an OR gate. And then let's first do for an OR, right? I've set the learning rate. I've set some max iterations. I've initialized the weights to be random, right? And the bias also randomly. I've set the sensitivity of the sigmoid function. So I've taken a sigmoid function, which is nothing but 1 by 1 plus exponential of minus lambda x minus bias in this case, right? Because the input is coming here. And in fact, one thing I sort of forgot to mention, and I want to do that right now before we move forward. Let me just come back here very quickly. So if you remember, if this is the perceptron, right, which is nothing but y equals f of, in this case, w1 x1 plus w2 x2 plus bias, correct? Or minus bias, or whatever it is, doesn't matter. Now, what is this part? Can anyone tell? What is this an equation of?
Linear combinations of with parameters.
Yeah, but what is this? What is this an equation of?
Line.
Line, right?
Yes.
Yeah.
Linear plane.
Yeah, this is a line.
Yeah.
So if you take your input feature space x1 and x2, right? Now I can write this entire thing in terms of x2, right? So if I take this as a line, this is w1 x1 plus w2 x2 plus b equals 0. So that means that I can write this as, in terms of x2, w2 x2 equals minus w1 x1 minus b. So x2 will be minus w1 by w2 into x1 minus b by w2. So what is this form now?
Intercept from slope intercept form.
Yeah, y equals mx plus c, right?
Yeah.
So where this is your y, this is your m minus w1 by w2, and then this is your intercept minus b by w2, right? So that means that at the end of the day, what we are going to get is a line that is going to separate out our feature space. In essence, that if these are the three classes that belong, if this is the three inputs that belong to the same class and this to a different class, we should see a line that's being drawn with slope W1 by W2 and with an intercept of, in this case, B by W2. Right? So we should see that happening, right? So we should get this, and that's how you are able to separate. That means that when you feed this input, this line sort of separates out whether the value of the sigmoid is going to be 1 or 0, right? And this line has to be somewhere in between these two classes in order to get that output distribution. Is this clear? Right? When we think of this line, we think of it as a separator. That basically means that any value that you give that is above this line, the output is going to be close to 1. And then any input that you give that's below this line, it will be close to 0.
So, sir, like in
And
this
this-
sense, what is meaning of here biased B?
Bias is nothing but the way the intercept works, right? If there was no bias, then this intercept won't be there and you might not get this separation out, right? Yeah. So when you say minus W1 by W2, only if you don't have the bias, this curve, this line will be always here, right? It will go through the origin. But that's not what we want. We want these to separate out. So when we add that bias, this line will shift here, right? In fact, we will look at the code, exactly this. I'll show you. If we add the bias and if we don't add the bias, what happens? Okay. Everyone on board with this? So
Yep.
if you understand this, let's now go to the script and I'll tell you what I've done. Okay. So basically I've initialized the weights, initialized the bias, initialized the sensitivity of the sigmoid. When I increase the gamma, the sigmoid becomes more non-linear in nature. That is, it becomes more sharper. The transition, right, between 1 and 0 becomes more sharper. But if I push it close to 1, then it becomes much more shallower, right? Now, these are my predictions. I'm taking my, this is passed through the sigmoid function. I take my errors, which is output desired, whatever I want, which is the OR gate, minus my predictions. And then I basically take my weights plus some learning parameters times errors times inputs. So eta delta, which is d minus y, times x. Okay. And then the bias is nothing but bias minus eta times my error, y minus. Okay. So that's basically it. And then the weight update, I'm just storing the weights and biases and so on, because I want to plot this. I want to plot the slope of the line as well as the intercept, which is bias by weights and weight minus weights by weights too. And I'm going to plot that. And you'll also look at the error function. So you'll have two plots, one where the input space is shown, where you'll have your points and the classes of the points. You'll have the line that's being fit, and then you'll have the error function as a function of the number of iterations. So we should see, according to this algorithm, the error function should decrease across time. So let's run this. I'm gonna run this section first. Okay. And now I'm gonna run this. And hopefully people can see this. Okay. So in this case, this is how the perceptron is training now. Now these are the 3 different points that belong to one class, right? This is belonging to another class. This is your error. And this is the line or the hyperplane. In this case, it's of hyperplane in 2D is a line that is separating these two classes out, right? And you can see that as a function of time, the error decreased. right? So this is where the gradient descent is working. So your now outputs are being predicted well for the input cases that was presented, right?
One question here, sir.
Mhm.
So now, if you would increase the bias,
Yeah,
the red line, the separator basically
red
would
line would
shift
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 above,
closer to the origin, right? If we
closer to the
increase the bias.
origin or not. So if I remove the bias, let's say I remove the bias, okay, I don't have any bias, I'm not going to update the bias, I'm just going to put, let's start with 0 bias, okay, I'm just multiplying 0 here, and then I'm not even updating the bias, okay. So if there is no bias, then what we should see is that the line should now merge only at the origin, right? It should be at the origin. So you can already see without the bias, the network is suffering to learn, right?
Right.
It's not able to understand that, that it can classify. So it's now in some other space. So slowly it will converge, but it will still be bad. It will turn and then it will come here. It will take some time. By the time 200 iterations will be done, but it'll slowly turn and then it will come here, right? But the minute we add the bias, right, in this case, even bias can be initialized at 0. But if I just train the network, yeah, the minute the bias is added, you'll see that the network pretty much learns, right? So in this case, the bias is very important because you need to be able to separate out these inputs from here. So the line has to have an intercept. Only then can this be above the origin. Okay.
Okay.
Now let's take another example here.
Sir, one question.
Yeah, of course. Go for it.
When we not updating the bias,
Yeah.
at that time we also updating the weights, right?
We are still updating the weights. Yes.
Okay, so in
Yeah.
that case also we didn't get a.
We couldn't. The network could not learn the problem. Right.
Okay,
Yeah.
so bias is important.
Bias is important. Yes, bias is very important, especially in these classification problems, right? If you can imagine, right, in 2D itself, you need the bias. In like an n-dimensional space, you need to be able to intercept the exact axis in order to create that line or a boundary that will be able to separate out classes, right, in that n-dimensional space. So the 2D kind of gives you the intuition that this is important. Okay. Now,
Sir,
mhm.
sorry.
Yeah, please.
The bias actually takes into account the sum of errors, while the weights have only errors.
No, wait. I'll tell you. Here, right?
Yeah.
Okay, so here I think so output minus desired, where my errors are, I think, just, I don't think I even need sum, right? Did I, am I taking it for all possible? Yeah, see, here I think the math works out because it's doing dot product. I can even replace this with this, right? Right here, I need to sum it up. Yeah, because when I do error times inputs, I'm basically doing dp minus yp times each x, and then I'm adding all of them up, right? This operation just does that. In fact, I can take this operation and then replace it with this, and it will still work. I'll show you.
Sir, you are running for each iteration, right, sir? So there is
Yes.
no need of sum there, I think. If you without sum also it will run.
No. What I'm doing is for every iteration, I'm feeding it all 4 inputs. Yeah. So in this case, I'm saying that this. So in the other words, this iteration is kind of like an epoch. I'm given a given epoch. I'm feeding in all 4 inputs, right? So at every instance, I'll get 4 errors. 4 errors. Yes. Yeah. So a better word would be epoch here. Right? For every epoch, I'm feeding in all the 4 inputs. I'm getting their errors from the network, and then I'm summing all the errors here, and then I'm so this will also work. So if I run this, that's the same as that. Okay. All right. So that's a simple OR gate, right? Now let's look at the same thing, but this time I want to change it to an AND gate, right? And what will we see? Pretty much the same thing, but this time the line would come here, right? Yes. So now these 3 classes are separated from this. Yes. And there you have it, your AND problem being solved. Now, let me ask you one question here. I'm going to change this to an XOR gate. Okay. Now let's see what the network does here. Okay. Is this problem first linearly separable?
No, sir.
Yeah. No, right?
We cannot separate.
We cannot separate this out. So what do we need here then?
Activation function non-linear.
No,
Yeah,
we do
non-linear.
have that,
We
right?
need to transform the space.
Yes, we need to either transform the space or
Maybe through hidden layer.
yeah, we need to add one more layer to this. Okay. We need to add one more layer. Then what might happen is there might be a line that separates this out, and there'll be another line here that separates this out. So anything within these 2 hyperplanes will be one class, and anything apart from these 2 hyperplanes. So already can you see that how a decision boundary can change if you add the hidden layer? In fact, I wanted to add that into this script, but I could not find the time. But I hope you get the idea, right? In this case, if you draw another line like that, right, then anything within these 2 lines will belong to one class outside that. So now your decision boundary has become a little bit more complex than what we started off with, right? Now just by adding the hidden layer, right? So if you add one hidden layer with 2 neurons again, and then combine it to your output, you will get a thing like this.
But there is only single decision boundary, right?
So in that case, there will be 2 decision boundaries, because one which will be going to each of the hidden layers, right? So you have another hidden layer in there, which will make it now 2 decision boundaries rather than 1, right? Because you're projecting it to 2 neurons in the hidden layer. And that way, your decision boundary from those 2 neurons will be basically, you'll have two of them in that case.
So number of layers, if we
Yes.
increases the number of planes, right?
Yeah, and it increases the complexity of this plane or this line or in the boundary as well. And in fact, sometimes it even bends the boundaries, right? It can make any sort of any piecewise linear any non-linear function can be approximated by piecewise linear functions, right? So you can basically use all these small hyperplanes to create a very complex boundary.
But sir, just an intuition, I don't know if it's correct. To increase the non-linearity, we have got complex activation function which can do that.
Yes.
Right?
Yes.
So when we say that can we do that changes in the decision boundary use increasing the number of layers within the hidden segment of the neural network?
Right. Sometimes that's what people did, right? Initially, when they came to multi-layer perceptron, what they saw was, okay, we have a hidden layer. If we increase the number of neurons in the hidden layer, can we actually increase the amount of complexity in the problem. But they then saw that having more hidden layers worked better, because what they could do is that generate complex representations on top of each other, right? That's the idea behind the deep learning. You're sort of creating a hierarchical representation from very simple features or some primitive features that you are actually sending into the network, right? So there have been variations like that. We'll actually discuss it in a couple of slides now, actually, in fact, the next one.
So there are
But,
two
yeah.
things. One is, does the increasing number of hidden layers increases the number of planes, or
No. So increasing the number of hidden layers will increase the complexity, the shape of the hyperplanes, and so in sense that it's transforming the space, right? You see, it's not that you are increasing the number of planes. So for example, if you take a two-dimensional input and you go to a two-dimensional hidden layer and then one-dimensional output, which will you see in this case. Now then you insert two hyperplanes, right? Yes. Now if you take a two-dimensional input, go to a three-dimensional hidden layer, right? And now this time you start introducing one more hyperplane into the set. But when you add more hidden layers, you are transforming the input further and further. So you're making a much more complicated representation of the input itself, such that at some level the input could be separable just by these lines, right? At that level. So it's not just about, because certain problems even with 3 lines might not be able to separate out very well, right? There's a chance like that. So when you transform the input further and further by adding more hidden layers, there is a chance that at a certain level you are able to morph the input space. That's what we looked at in the first class, right? Like we are able to morph it such that at that level it's linearly separable. Okay, cool. Okay, guys, so
basically by increasing the number of hidden layers,
yes,
the dimensionality is not increasing, right, sir?
Yes. Unless you sort of increase that too, right? Like in some sense, you can increase the dimensionality too, but okay.
Dimensionality is increased. Then what is the?
What I'm saying is there is a possibility that can also happen, right? So if you have two input neurons and then you have 3 hidden neurons. Right? So now what you have done is you have gone from a 2D through a 3D, right? So for example, if the input space looks like this, you have set of points here and then another set of points in an annulus outside.
So your display is not visible
now. Can't you see my slides?
Yeah, we can.
Yes, sir.
Yeah. Okay. Now, if this was the distribution, right? Now this is a 2-dimensional space. In this space, probably it's not separable. By projecting it to a hidden layer which is higher dimensional than this, there is a chance that you can separate these two things by height, right? That's what we discussed even in the first class. So there are some advantages.
It will become a plane, right, for separation?
Yeah, then it will become a plane there. Yeah, it will become a plane.
Whatever we can implement using the kernel trick can be implemented using the deep neural network.
Deep network, right? Exactly.
Thanks.
But in some sense, if you do not know the shape of the kernel that you want to use, or the data isn't in the way that kernel methods are amenable, deep learning will give you an arbitrary kernel, right? That will be helpful in separating these two things.
Okay. So, yeah, sir, in a way, neural networks are flexible enough to increase the number of layers or perceptrons per layer.
Yeah.
But what they do is a kind of black box for us, right? In between.
So we can test some of the ideas of the black box. That is, we can test how the weights are, how the weights have converged for a given hidden network, and from that infer what that hidden layer is doing, right? In fact, in the first class, when I gave you the example of the faces and the lower level and the mid level things, that is basically a trained CNN, and you are looking at some of the trained weights of the hidden layers, that are there in the CNNs, which are giving you information about what likely that hidden layer is actually responding to. So there are ways to probe a deep neural network in such a way that you can understand what's going on, right? But at the end of the day, as you say, it is a black box, but there are ways to decode and get an understanding of what is happening. Okay. All right. Any other questions here? Because I think we'll start shifting gears a little bit and start discussing. Okay, yeah. So I need to finalize this. This is the backward pass finally. So coming back to our original network, right? Like with many hidden layers. Now for a simple perceptron, you got this idea, right? Like you have to take the error, you have to push it back through the network. But how do you push it back when the network has many layers, right? In this case, 2 hidden layers. And the concept is the same thing, okay? Let's say this is the error, right? This is the error at at the output stage, right? So you have the gradient of error with respect to your parameters, right? So yi minus ti in this case with respect to this. So what you're doing is you're pushing it through this node, right? That means at this point, right? What is the error that was obtained at this point? So this error y minus d minus y or y minus target or whatever it is, right? You push it through this. That means you have to push it through the gradient of the function that was of the activation function, that g dash of h, which is this term dy by dz, and then dou e by dou y1. So this is basically the chain rule. This is what often called the differential chain rule. That is dou e by dou z, which is what you want, which is with respect to your parameters, is nothing but can be written as dou e by dou y1, which is nothing but yi minus ti or y minus d, times dou y by dou z, which is going to be your gradient in the activation function. So if you take the error, push it through that, you get the errors here. So for similarly, you will get an error here, right? For these 2 neurons, you sum those 2 up, and that will be the error at this point. Okay, if that is the error at this point, you kind of push it through this node, that is the gradient of this node, then you get an error at here and here. Okay, here and here. Okay, now you sum these errors up, that is the error at this node. Okay, so this is how backpropagation works. So the error, which is y minus t at this level, is pushed through this network through a series of nodes, and after you push through this, you get the errors at this level where you sum up those errors, and that's the error which is then pushed through this node, so that you get an error here, here, and here. You sum up those and you push that error through this node, and that's how weights and biases at each level gets updated. Okay, so it's nothing but the same thing, but it is an extension through this entire network. That's about it. Okay, so instead of just doing y minus t times g dash of h, which will update just these 2, you take that same error, you sum it up for a given node, and then use and push that through this node, get the error at this level, and then you do that. And that's why it's called the backward pass. So you first start here, and then you propagate the error throughout this network this way. Any questions here? The math is nothing but telling you how the errors are getting summed up. So the error at this point is nothing but you take the weights at this level, you multiply it with the error that you got at this level, the gradient, and then you multiply with those respective weights, and that's where you get the error at this level, the gradient in the error at this level. Then again, you push it through the network like this, right? Once you get the error on the other side, you multiply it with the respective weights of that, and you push the error back, and that's this. And once you get the error at this level, you again multiply it with the gradient of the neuron at this, which is dy by dz, dyj by dzj, right? this one, and then you get the error at this level. So it is a way to just take the error and then push it back through the network, and you are using the weights themselves as a way to backpropagate through this.
Sir, what is the difference between Z and W?
So Z here is nothing but your parameters only, right? This can be a combination of both your weights and your biases, right? So Z is nothing but sort of a temporary
I think
dummy
WX,
variable. Yes.
WX plus B.
B. Yes.
And sir, dE by dZ is it's a delta W or
it could be delta W or delta B, depends upon what you are trying to achieve, right?
Okay.
But
And
with respect to your parameters, this is how the chain rule works. It's exactly the same thing, right? What we saw, but it's just that because here we have the error locally, right, available to us, it is there. But here we do not have that error locally. In order to get the error locally at this point, we have to push the error through this, update these guys, but then again push the error through this too, so that we get the error here, the local error here, so that we can update these guys, and then we have to get the error locally here, so we have to push those errors through this, and then you get the errors here too, right? So this y minus t now gets propagated throughout this network, right? And each stage you use this chain rule to estimate what will be the error locally at that node.
so we update the weights by that error, right?
Yes, change in the error, right? That's the gradient descent, right? So delta W is minus dou E by dou W. So in this case, this W is replaced by Z, right? So Z could be any parameter that you want to update, weights or biases. As I told you, right, there is typically separate bias is not because calculation wise, it's easier to absorb the bias into the weights. And that's why you see that you can write a neural network very simply as, f of W times X, right? So that first W and the first X is going to be your weights and your bias.
So just another question.
Yeah.
Is the like the error at the output node? So is that same error being
Very good
propagated through every?
Very good question. Very good question. That's the next point I was about to come. Have people heard of this vanishing and exploding gradients?
Yes.
Yeah. This is the idea that as what was rightly said, is the error that you get here the same as that here? Obviously no, right? It is some aspect of this error is being backpropagated, right? And this is sometimes the problem with training neural networks, right? Because the error, if you get at this point, is not if it's not propagating through this network, so that these nodes can actually feel that error, or feel the change that it's like sort of trying to push through a very viscous liquid, that you push it one side, the viscosity or the change in the force should be seen at this level, right? So sometimes what happens is that change is not felt here, right? Which is often called as vanishing gradients. That is, these gradients, when you multiply them, right, throughout this network, the error at this point might just vanish off, right? So the change in the weights might not be that significantly affected compared to what you see at this level, right? That's often what's called vanishing gradients. Sometimes the opposite happens. Sometimes the change in the weights depends upon how these initialized weights were, right? Typically what you want is that you don't want the weights to be initialized to a very high value. You want the weights to be random enough so that the sum of the weights equals roughly equals 0 at a level. So all that stuff you typically take care. But if you do not take care and the weights are sort of initialized to be very high, then this error will get backpropagated, and this change at this and that will multiply, and sort of there'll be a cascading effect where it will just snowball, and at this level the weights might just explode, right? That's the idea of exploding gradient. That is, you add too much to weight change. Delta W is too high. And that way, the way the network does not stabilize at all. It just blows up and, you don't get the answer. Right? In fact, in our perceptron case itself, we can demonstrate that. If you initialize the weights to be too high, right, then, your initial estimate of where you are itself is completely wrong. So you're just gonna not be able to solve the problem. Right? And then sometimes it's vanishing. That means that if you start it off in such a way that, the change in the weights is not being felt at this level, then there'll be no changes in the parameters, and thus the network will not itself get trained. Yes. So these are the issues. And yes, it depends is the answer to that question, right? It's not the same error that is being felt at every level of this layer. It depends upon how the network was initialized and how the errors are being propagated throughout this. So that's how it works. Okay.
Sir, I have a question.
Yes.
This error we are back propagating, having any impact on the original input?
No, inputs won't change. Your weights and your biases will change, right?
Yeah, but in between there are hidden layers, right? Hidden nodes, they are manipulating, right? Sir?
No. Hidden nodes, they are not manipulating. They're just manipulating. So what will happen is that the activations of the hidden nodes will change the next time you do a forward pass, right? Because your weights have changed. Okay. But it won't change the activation, right? It's just going to remain the same. Okay, the parameters will change. It might change how the network reacts the next time it receives another input, but it will not change the characteristics of the nodes themselves, right? It changes the parameters, which will then change how the node behaves in some sense. Okay. But the way when you're back propagating, you're only changing your parameters, which are the weights and the biases. Okay. Hopefully that's clear.
Sir, what is the purpose of back propagating this error?
Yeah, so you want to find out a way in which the network can start predicting close to the target, right? Now with we saw with this perceptron example, it was very easy, right? The y minus t, which we pushed it through the network, the next time the network was able to learn very well. In fact, what I did not show you is the output, right? At the end of the day, when I pass the same inputs to the network, it will predict the right output. That's what we want. We want the network to learn some task in this case, right? Like mapping inputs, outputs. That's what we want. And what this backpropagation does is tells us a way in which this network can be trained so as there's a better mapping between our input and our output space. Right? So input can be an image, output can be the class of the image, for example. That's the problem that we want to solve. But we want to also ask the question that, okay, if I train it like this, will it generalize to classes that was also to classes that was not presented to the network, right? That's a different question of generalization, but initially you do want to train the network so that on the information that you presented, it does reasonably well.
And is there any way that something we are defining, like how many times we are back propagating this error?
So for every input x, right?
Yeah.
Yeah. So or a bunch of inputs to xn, we can use that information.
So in single training, like how many times we
depends upon the number of things that you give, right? Like in our case, in the perceptron case, we saw I gave 4 inputs and then I got 4 errors and then I used that to update the network. In this case, I can get n images and I get n errors and then I'll backpropagate.
I think that is based on the number of epochs, right?
Epochs as well. Yes. Number of epochs and how many information you have within an epoch too, right? Yeah, so in a given epoch, you have certain number of samples of your inputs, and for that you'll have one backward pass. and the number of epochs increases, you'll have that many number of times. At the end of the day, you are trying to minimize some objective function, right? So you'll see that, okay, whether the objective function has stopped changing, whether it has minimized, right? We looked at that. Okay. Cool, guys. Let's move on. What is the time right now? Can anyone let me know quickly?
11.
It's 11 o'clock.
11. Okay. So we have 15 minutes more. Let's quickly finish this part off. And with that, we'll be done with the introduction so that next week we can start off with looking at interesting deep learning architectures. But before we go into that, I want to establish what are the available deep neural network architectures, what sort of problems they are trying to solve, right? And what are the things that we saw right now. Now, it is often important to understand feed-forward networks because they are the basis, right? That's how things started. Because all of deep network is basically understanding what forms of architecture can be used to solve a specific problem, right? And why it is a very rapidly evolving field is because the type of architecture changes, right? There could be a paper out right now which says that something that you tweak in this deep forward network can improve the performance, and suddenly that becomes textbook later, right? And that's why it's a very rapidly evolving field. And if you're not updating yourself constantly, you kind of get lost in what is the state of the art currently. But to name a few, these are the ones that are out there, right? So we looked at a perceptron, we looked at feed-forward networks. There's something called radial basis networks. Anyone know what these are? Radial basis? No? So instead of mapping on to an activation function, instead of the hidden layer being activation function, hidden layers are what's called a radial basis functions. So they can be Gaussians, which will be mapped to, say, a specific mu and a specific sigma, right? Standard deviation and mean. That means that you're taking the input space and mapping it onto a distribution, right? Like in neuroscience, there are these very nice experiments where people have looked at what's called tuning functions, right? What they have done is that there was Nobel Prize winning work where in cats, they recorded brain activity from the visual areas of the brain, which responds to vision. And they presented the cat with bars of different orientation, right? Like what bars of light, right? These are just visual stimuli, right? And then they change the orientation. So this is, say, this 45 degree, and then 0 degree, and then 90 degree, and so on, right? And what those neurons started doing was showing tuning curves. That means they showed a pattern like this, where for a given orientation, say for example 45 degrees, they showed highest activity, and then the rest they showed lower activity. Okay, and these were very interesting because it looked like if you use these networks, they can become really good what's are called universal function approximators. That means, any idea what that means? Anybody? What's a universal function approximator?
Can be applied to any orientation. Yeah.
And then it can capture any type of function, right? That means any function you come up with any arbitrary function. This sort of network will be able to approximate that function. Okay. Because of its nature, that this is how it is set up, right? It operates like, instead of operating as a node with some activation, it operates like a probability distribution, right? With some mean and some variance, which is how the network is mapped. So these are often called radial basis networks, which are used for this. And an extension of this is what we see as deep feed forward networks, right? Like we have multiple hidden layers, so there is a hierarchy of representation. Typically, this is connected all to all, right? And that way we can start solving a lot of these problems where there are complex nonlinear boundaries.
So one question, like in radial basis network, so only like this, what they have follow this normal distribution basically.
Yeah, but there could also be other type. There are other types of basis networks as well. Radial basis in the word is in basis. So that means there are certain basis functions that you can use, right? And basis means these are functions which can be used as a basis to get any other function, right? That's why they're called basis. So you might have heard in mathematics, these are basis functions, right? So idea is that these sorts of functions can, if combined in the right way, can give rise to any form of function in the world, right? You can even approximate, if you want the network to approximate even a step function, it'll be able to do that, right? So any type of function that you think of, this will be able to approximate, right? So that's the idea behind the radial basis function. The idea of radial is that there is some mean followed by some tendency, right? A Gaussian sort of fits that bill very well. So often for radial basis functions, you use this. You use Gaussians or normal distributions as the basis functions. Right?
So what do you mean by approximating a function? Like
approximating a function is, let's say I have a function like this. Let's say this is my x, this is my y, and I have a function like this, right? Can you write an analytical form for this function? That is, can I write something like y equals sine x plus 4 cos x, something like that? Can I write something like that for this? No, right? Because I don't know, this is some arbitrary function. Maybe you could, but who knows? But what that network might do is it train itself in such a way that it can reproduce this function in some. Okay. Yes. So that's a function. Yeah.
Sir, so just like understanding the input and output, it can train itself to make to approximate any kind of arbitrary function, right?
Yes, it can, but these are a specific type of way of doing it, and there are certain advantages to doing it with radial basis functions. I don't want to get into the details too much to guess, because that's an entire conversation on its own. But the point is that since these are smoothly varying functions, it's easy to change and also even generate new functions out of it. I'll talk about this a bit later, but yes, even such deep networks are universal function approximators. But often when you are thinking about universal function approximators, you think of networks which have certain basis functions which can give rise to, all of these things. But yes, even a simple feed-forward network can do this. But I'm just giving you an example.
Sir, so can this mean that any network can actually be a classifier and a generator in a same architecture kind of thing?
Yeah, I'm gonna show you some examples in the next one. Yes, exactly. Very good sort of observation. Yes, it can be. Okay. But there needs to be specific conditions that need to be met. I'll show you how that is. In fact, I'll show you some autoencoder architectures which can do that. Okay. So these are one type. Okay. Then, which we look at in detail in the coming classes, are the forms of recurrent neural networks, right? Recurrent neural networks, by their very nature, are recurrent. Okay. That means recurrent is that they are basically either self-activating or activating other neurons in a layer, right? So that means that there is some feedback, okay, and that feedback helps in maintaining past information as well. That is, whatever output that is coming from the network is fed back to the network or to the layer, or from other layers back to the same layer, right? For example. So this is the way that you can see this line here, right? So in some sense, information that's coming here is feeding in back to the same area. So there is feedback. And because of the feedback, there is some amount of memory in this network. That is, it is remembering a small amount of the past. And sometimes that's important to make context-based decisions, right? Like if there is a sentence, the cat is jumping over blank, right? Now, if I pass this sentence out, I need to understand that it is a cat and it's jumping over something, right? Now that means that if the network does not have a history, it does not understand this context. And in fact, if the history is shorter, then the word that if I ask it to fill this thing might not be meaningful, right? So the idea of recurrence is that information feeds back into the network in that same layer, or past information feeds back, so as to give the network memory-like properties. And then there are variations of the same, often long short-term memory or gated recurrent units, which are a way in which you specialized architectures that you arrange the network in a specific way that seems to have more benefits to helping the network learn or understand information that was way back in the past, right? And how much back in the past, that depends, but more than, say, normal recurrent neural networks. Okay, so there are ways to do that. We will look at this in detail in the coming classes. And then there are autoencoders. Any idea what autoencoders are? Anybody? What sort of class of problems are they trying to solve? At least from this
unsupervised learning.
But what are they doing?
Basically, helps us to learn the unlabeled data.
Yeah. But in sense, when you say learn the unlabeled data, what are they actually doing?
They're kind of mapping the input and mapping it to a different space itself.
Yes. So it's mapping in this case to a what space?
Low dimensional.
Yes. Very good. So it's mapping it to a low dimensional space, right? That means it's encoding the information into a space that is low dimensional in order to find out what is probably the relevant information in this input, right? So in this input, what are the things that I need to keep? What are the things that are irrelevant? That if I take that same thing and reproject it out so that the input matches the output, right? Can I reconstruct the input with minimal loss? Okay, it's often what's called a reconstruction loss.
Just like PCA.
Exactly like PCA. But in PCA, the rule is like there is the latent space is orthogonal to each other, right? The component space that you come up with, right, are orthogonal because principal components are orthogonal to each other. But this does not need to be that. It can be any latent space which will preserve the information of the input so that the reconstruction loss is minimal, right? So in fact, what people have done is all the traditional machine learning approaches where people have come up with theories that, if I want to maximize variance, if I want to maximize independence, there are specific type of methods. What they have done with deep learning is gotten rid of all that, saying that I don't want to hand tune anything. I will let the network figure it out. Okay. And in this case, the network figures out what relevant information to keep, right? And then when you test what is happening at those level, you get an intuition about what is the network doing in order to minimize the loss, right? We might not have even thought about doing it that way, whereas the network is able to come up with that. That's the idea, right? Okay. But what is the... Yes, was there a question?
So, but like how, like what is the idea behind like network?
So the idea is simple, right? The idea is that you want to minimize reconstruction loss, right? That's all. The objective function is to minimize reconstruction loss. Minimize this. And you let the network figure it out, what it needs to do. Okay, you constrain the network in terms of how much the low dimensional space has to be, and with that given space, if I have to minimize the reconstruction loss, what is the latent space that the autoencoder comes up with. That's the idea behind these forms of models. Okay.
So how many?
Yeah. Sorry.
How many dimensions we have to reduce it to?
That depends. That depends entirely on the problem. We can't just fix that. This is just a representation. But most of the encoding models that you might have seen, right, use this sort of an architecture, right? Encoding models are basically ways in which you have a compact representation of the input to preserve the relevant aspects of the input, right? Those that are important, those that have some meaning to it in order to do other stuff.
So, sir, like one doubt here, like why we want to reduce the dimension here?
Yes, in fact, that's a very important question. Can anyone attempt that answer? Why do you need to reduce the dimensionality?
One case could be where
image compression.
Huh?
To reduce the network bandwidth.
Yeah, data bandwidth is one thing, but you
Computational power also.
Yeah, computational complexity will be reduced. Yeah, you can do
to remove the unnecessary features.
Absolutely. So there are going in an image, for example, there might be so many pixels that have no relevance to the output problem, for instance, right? So you don't want to use all that. You just want to keep stuff that is actually important, right? So that is the reason why you want to reduce the dimensionality of the input sometimes. Sometimes you can't even handle. Okay, I'll give you an example. If you want to play the game Mario, right, which is, you know how many states Mario has, the game Mario? Anybody have an idea? Game
9,
states? Sorry?
9, I believe.
No. Game states. When I say game state, every frame where the agent is a state. It has around about, I believe, 10 to power 29 or something like that. That many huge number of states it has, right? If you want to parse all that information through a network to make it play such a game, let's say, for example, right? You need to be able to reduce the dimensionality of the input, right? In order to do that, so that it's computationally more efficient, right? And it's able to retain. I believe this is somewhat the number. I don't know. I might be wrong. Yeah. So just don't quote me on this. But there's like a huge number of states. I know that. But what I'm trying to say is that that's the relevance of such models. Okay. And in fact, reconstruction is also another example for such low dimensions. That is, if in this low dimensional space, with that, if you can pick one latent space and reproject it back, and you start reconstructing information. Yes. Yeah.
So as we with numerical data, as we use some methods like GMM, like Gaussian mixture model to fill out all the data that are most likely to be whatever we are putting the input in. So I think it will be exciting to see like how autoencoders use it for the image data to fill the space.
Very good. That's nothing but a variational autoencoder. In fact, you just gave me a very nice segue to go into the next one. A variational autoencoder is exactly what you mentioned, in sense that instead of projecting it onto a space or encoding it onto neurons, you encode it onto a multivariate distribution, like a Gaussian mixture model or whatever it is, multivariate.
Okay.
Sir, can I ask one question, sir?
Of course.
Yeah, sir, CNN is also doing like the pooling layers of CNNs. They are also doing such kind
dimensionality reduction. Exactly. Yes, they are also doing it, but they are somewhat spatially preserving the information still, right? Here, the information is still getting mixed completely, right? So there are certain differences there.
And sir, I also want to know where transformer architecture should come after VAE, GAE, or before that?
Correct. So there are two ways to do it. One is to use an autoencoder like architecture to actually do the encoding first, and then you can have the transformer architecture. Or the exciting ones are actually the variational AEs. I'll tell you how they work, but it's very interesting to see these sorts of architectures, when they combine, they become a lot more powerful. But yes,
because sir, image compression, what maybe I am wrong also, image compression we are also doing in CNN also, through CNN.
Yeah. Of course, that is also a way to do image compression. In fact, image encoding can be done through layers of CNN, and finally, before instead of having a fully connected layer at the output, you can take that as an encoding of the image, right? The final output of the CNN even before you reach there. So that's also a way to encode. Okay, it just depends upon what sort of problem you're trying to solve, right? Like for an image, you would better use that. In fact, the next thing is what we are going to talk about is that. But what is the time, guys? I think we might slightly be
11:18.
Yeah, so if you give me like 5 minutes, but I guess this is a very nice discussion that we can extend it to. But if you can give me 5 minutes, I'll just go through that. But if you have any questions, just hold it on to the end, because I can be here and I can still discuss. But let me finish that for the sake of others who might want to leave as well. Okay. So variational autoencoders are those where instead of projecting it onto sort of a space where you just encode, you project it onto a space which is probabilistic. That is, you do a multivariate distribution. So instead of mapping it onto a neuron with some activations, you map it onto a distribution having a mean and a standard deviation and so on. Now, what this does is, interestingly, at this level, let's say if this is my latent space, for an autoencoder, if the latent space is very discrete, right? Let's say I have another information. Right? If this is my latent space of two clusters, what the variational autoencoders do is they can smoothen the space out. So instead of looking like this, it'll look like a smoothed version of this. Okay. And that way, it also has generative properties. That means you can move within this space and get variations of that same input. For example, if the input is an image of 0 that you are getting, and you are getting an output as 0, right? By using a variational autoencoder, if you change in the 0 space and move in this, so this is now a probability distribution. There is some mean here, right? And some spread, right? In every direction. Now, so what this will do now is it will create a smooth version of the output. So you can maybe even change the 0 to a different type of 0, or 0 written differently. To give you an example, there are all these apps, right, where a person is, inputting his photo, and then output comes a photo with glasses, right? Something like that. Yeah. So what this is doing is, in that latent space, you are moving towards a space where you have trained it with people with glasses. So this smoothness in the latent space gives you a nice way to move between these two different latent spaces, right? So that now you get a person with wearing the glass, right? And you don't get like a very distorted image. And to kind of very quickly speed it up, we have things like denoising autoencoders, where the inputs are provided with some noise, right? And that way, the training becomes better. And then you have like sparse AE, where the input, instead of in the hidden layer or the middle layers, instead of being low dimensional, can also be high dimensional. So now there's sparse encoding. That means some can be ones, the other can be zeros, like, or most of it is zeros, only some of it are ones or high value, for instance. And sparse matrices have certain properties which we can utilize, but not to delve into too much details. We'll also look at deep convolutional neural networks. This is something that people are very familiar with. They know because these are pretty much used everywhere. People might also have thought about deconvolutional networks. That is, you go the other way around. That is, from the low encoding representation of the image, you can go to the lowest level features and actually display the image, right? So this can be used for image generation. And then there are deep convolutional inverse graphics networks. That is, you basically first give a set of images, it goes to a latent space, you can modulate this latent space and create variations of the image, right? So it also has, and in fact, as someone was mentioning, right, can these networks be manipulated to have generative properties? This is an example of that, right? So you can change the nature of the image here at this latent space, and then when you reproject it back, it has different properties here. Okay, so that's that. And then there are general generative adversarial networks, liquid state machines. People must have heard of GANs. GANs are these very current models that are used for generative AI, right? Now the way they work is basically there is a guy who's basically taking in random noise, right, input, okay, and then generating some initially some junk data, right? And there is another network, right, which is basically the sort of the teacher network, right, which is trained to produce the right things, okay? And then when these two guys compete in a sort of a way, the idea behind the adversarial part is that they compete. That is, this teacher compares what this has done, and if it is not something that is similar to the real one, then it penalizes this, and so on and so forth. So there is a adversarial way in which both of these are trained in sense that at the end of the day, this starts producing something realistic, right? Not this junk. Yeah, and then that way you can start generating with just some input noise, different types of images, different types of outputs that mimic the real world data. So for data augmentation, these sorts of networks are very helpful. And then there are other types of networks which are recurrent in nature, but which have a specific underlying network structure. Yeah, there are liquid state machines, echo state networks. In fact, I worked a little with echo state networks in my PhD, where this hidden network, right, this layer, will have a specific type of architecture and specific type of weight structure which is fixed. So weights are fixed, right? But they have certain properties. For example, you can change the properties of the weights in such a way that if you give an input, it will behave like an echo. Or if you ping the network will have some residual echo state. You can think of it something like the surface of the water, right? Like if you touch the surface of the water, you create ripples, right? And the ripples last for some period of time. You can create a weight matrix which has very similar properties, and that can allow you to solve certain problems which are, say, transient in nature, for instance, right? Like they are very, they give rise to information that is very short-lived, and with that, is it possible to explain certain phenomena, right? So, but these are certain variations of that. But I think you will be learning about GANs later in the course. But I think with that, I want to stop. You guys kind of know this, applications in different areas. There are vision CNNs, language CNN, RNNs based. You can take an image and then tell you, oh, this is a group of people at a shopping market, or a woman is throwing a frisbee, and this is the idea of even attention in this network. That is what area of the image that the network is actually concentrating on, right? So this is a representation of that. And then in medical image classification, CNNs have often been used to do segmentation, leak detection, mammographic mass classification. There are many things, and so on and so forth. Okay, so I think with that we will stop. If there are any questions, I'm happy to answer. But that covers our introduction. So next time we will start with CNNs. Okay.
Sir, what are these spiking hidden cells?
Where here?
Yes, sir. The green circle and inside there is a
spiking hidden.
triangle.
So spiking hidden cells these are spiking neuron models. Okay, there are neuron models where instead of activation functions, where instead of the information being coded as a rate, That is, if you can imagine that for an activation function, right, like a sigmoid, the input will tell you how active the output is, right? But another way to code this would be in the frequency space, right? For a given input, I can imagine the neuron to show spikes. Okay, so if the input is high, then there are more spikes. Or the input is low, then there are less spikes, right? So you can train this, or you can have an activation function like this, right? This is what's often called spiking neuron or spiking neuron cells. So instead of them having a rate, they are in terms of frequency encoded. Right? So the number of spikes give you information about how strong the input was coming to them.
Are there any special use cases where we use these?
Yeah, there are many types of spiking neurons. In fact, the ones that are, have you heard of quadratic linear integrate and fire neurons, QLIFs? Yes, these are types of neurons that are used typically to replicate spiking. These are called spiking neuron models. Yes.
Sir, I have a question. I have always thought about this, that all of these architectures are kind of similar, and by adjusting a little bit of this nodes and stuff and everything, the use case changes and everything changes.
Absolutely.
So how
how do you come up with this?
Exactly how this all this thing it happens, like how
exactly. Yeah, that is where the deep intuition behind the problem comes, right? Let's take an example. How did CNNs evolve? Do you know how CNNs evolved? What was the inspiration?
So basically, when we have an image, if we unwrap that whole image into pixels, it is extremely tedious and extremely hard to encode everything as an input layer. So for that reason, maybe to get the main features out of that images, we use that CNN architecture.
No, that is a consequence of the understanding there, but the inspiration came from the brain. In fact, our brain's visual system.
Okay, that's it. Okay, understood.
Yeah, the intuition came from here. The fact that there was already evidence, right? When I talked to you about the cat and the orientation stuff, people already knew that neurons have what are called receptive fields. Okay, so if for a given image, if you take a neuron in your retina, right, that looks at a very small part of the image, right? And if you go to an area which is slightly higher up in the brain, to an area called the thalamus, those have slightly bigger receptive fields. And if you go to the visual cortex, which is the part where the brain understands vision, those are much bigger visual fields. So this was the intuition behind this, right? That means you do not have to look at the image at the pixel level. You can construct an architecture that can inform about specific parts of the image, and the features can build across the hierarchy, and that gave rise to deep convolutional networks, right? That deep intuition about the fact that this is how image is getting processed in the brain, number one, and so on, right? For example, let's take the autoencoder case. Okay, there were all these machine learning ideas from principal component analysis, independent component analysis, every type of latent component analysis, generalized eigen decompositions. There are many methods which does dimensionality reduction. But the intuition was all of them require a specific objective function that they are trying to minimize. What is the objective function that you are trying to maximize, for example, in PCA? What is the thing that you're trying to maximize?
So we are trying to expand the dimensions.
Variance, yeah, very good. Yeah, we are trying to maximize variance. In independent component analysis, what are we trying to maximize? We're trying to maximize their kurtosis or skewness of a distribution, because independence basically is relying on the fact that the individual components are less Gaussian than the mixture. Okay, but forget about the math part. But idea is that there is a statistical quantity that people have designed that is used to maximize. Then the question came that why do you have to handcraft these things, right? Is there a way, because I know that when I take an input and I project it onto a low dimensional space like this, is there a way to use this property that we have found out, right, which can help us train these networks, right, to do a specific task? In this case, reduce the dimensionality. I don't care how it does it, as long as it does it with reasonable level of accuracy. Okay, and that gives rise to these autoencoder type networks. See, the intuition comes from an existing idea about what you want the outcome to be. It's very clear, right? See, deep networks are not formed because, okay, we just randomly stumbled onto them. They formed because there was an underlying need to solve a specific problem, be it image classification, be it some sort of prediction, right? And there are certain principles that underlie that intuition. When it's about time series prediction, let's take a time series example, right? You have a set of information about a pattern of activity. Now I want to predict what's happening at this time point, if this is time, and this is something like my weather or temperature or something like that. And I want to understand what's happening here, predict. What is necessary for this?
Previous time.
Yes,
like
yes.
the
What
link
has
between.
happened in the previous time points? That's important. That means that you need something that can hold memory. Okay. The machine learning alternative for these are what are called autocorrelative models. That is, it tells you if I take a section of time here and I take a section of time before and I correlate these two things, okay, can I get an estimate of how different or how same those two events in time are? Okay, and if I take a next section, can I then compare it with some previous section and make an estimate of what is going to come up with? Okay, this is a machine learning way of solving these. These are called autocorrelation models. These are used for prediction, right? But come to the deep learning equivalent of it, right? What do we need in this case? We need that there needs to be some way in which things in the past can interact with things in the present. And the way you can do it is come up with an architecture that has some feedback to it, right? Then the minute you introduce feedback, you get this property that it holds on to past information. But how long and how much, that depends upon the type of network. And that's where research comes in, right? And so we start improving. But the intuition develops from here. Right? So it's always wedded to what sort of data that you have and what are you trying to do with it. That decides the intuition behind how to develop such deep learning models, right? Yes. Even in this case, the idea was, is it possible to make a network generate? Even in autoencoders, they knew with variational autoencoders, this was way back in 2014, by the way, right? 2014 was when variational autoencoders came into play. Google and I think with Qualcomm developed this, right? This idea. But that was still generative, right? But then generative adversarial networks came a little bit more after that. And they understood the drawback behind those methods in such a way that they are not producing something that's more realistic. Now, how do we produce something that's more realistic? That means we need to compare whatever we are sending into something that's real, right? And that's where things start emerging, right? And that's where you start thinking of architectures that will give rise to a specific type of behavior from the network. So you should treat them as like, you should treat them like as if they are certain agents, right? Like a people in some sense, right? Now, how can I make the person learn something, right? Either teach it to them or either show them, right? You're pretty much doing the same thing with this network, but you're playing around with how the network is organized and structured in order to give rise to certain properties, right? So hope that made sense to everyone. Okay, guys. All right.
Thank you, sir.
Thank you. All right. So I'll see you guys all next week. I'll upload all these slides tonight and stop recording.